Good afternoon and welcome to Liftoff webinar today, where we are going to be speaking with Christopher Melnick, who is the Director of Business Development for California Nanotechnologies. Thank you for joining us. I would like to remind all the attendees to please submit questions during the presentation. We will be having Q&A at the end of the presentation, so please use the question function. We would appreciate that. So it is my pleasure to introduce our presenter today, as I said, Chris Melnick, who is the Director of Business Development for California Nanotechnologies, also called CalNano. Christopher is the Director of Business Development, and today he's going to be sharing the introduction to Cryomilling and spark plasma sintering. So thank you for joining us and look forward to a great presentation.
Welcome to Liftoff Webinars, brought to you by LIFT, the National Advanced Material Manufacturing Innovation Institute, where we drive American manufacturing into the future through technology and talent development. LIFT is a public-private partnership where we convene and connect government, industry, and academia in the fields of advanced materials, manufacturing processes, systems engineering to enhance America's manufacturing competitiveness, national economy, and national security.
Well, hello, and thank you very much for that wonderful introduction. So my name is Chris Melnick. I am the Business Director at California Nanotechnologies. Today, I'm just going to be covering a brief introduction to our two core technologies, Cryogenic Milling and Spark Plasma Sintering, also known as Field-Assisted Sintering Technologies. But before I do that, I'll give you a little bit of a background in what CalNano is and where we come from and what we do. So basically, California Nanotechnologies is a research and development and commercialization firm where what we do is we help our customers materialize their material science dreams. We help develop material science as well as components made from advanced materials, helping leading companies, one-man startups, national labs, universities, and everybody in between. Where we actually started is an interesting story. So it's kind of funny where we actually started off with shoes and rocket science at the same time. And so we actually were spun off from a company called Omnilight, who was one of the first companies to ever commercialize a metal matrix composite, meaning a material that has a metal matrix that has ceramic impregnated in it. The purpose of those was to essentially get the performance of a steel spike, but with the weight of an aluminum component, which otherwise would not be strong or have enough wear resistance for that application. When Nike approached the company back in the early 90s, they wanted to make the world's lightest shoe for this up-and-coming star called Michael Johnson, who was the favorite athlete for the 1996 Olympics. And therefore, that was a huge success. And of course, the company then diversified into aerospace and automotive applications with their cold forging technologies. At that time, our founder, David Grant, decided he wanted to repeat that success, and he really saw the awesomeness that was marrying this advanced materials technology with established production technologies to really make a new impact and have a bit of a paradigm shift in some of the established large volume commodity markets. So therefore, California Nanotechnologies was spun off and birthed from that, also with a company called Due Diligence Cryogenics, that's the cryogenic milling part. And some of our first contracts were working with Adidas to make the now still world's lightest track and field shoe, which had the metal ceramic nano composite spikes, as well as working on hypersonic materials. At this time, it was heavy cobalt-based superalloys, working with rocket engine manufacturers, as well as one-way payload delivery systems. So how do we work with our customers? We essentially work really closely, and one of the things we get the best grades from our customers on is that we really integrate well with your research and development teams. We essentially operate as a branch or a research department, developing new materials and systems, as I mentioned. We also have a nice host of additional capabilities that are not as unique and rare around just prototyping, testing, manufacturing of subcomponents, and things of that nature. So diving into it, cryogenic milling. So what is that and how does that work? So essentially here's a very rudimentary kind of diagram of what a mill setup looks like. The type of cryogenic milling we do is actually high energy attrition milling that is done in a cryogenic slurry. So essentially here, similar to a drill press or a mill, you have a large torque and rotating inertia put into the system, which is then churning the grinding media. That media can be made out of anything from stainless steel to tungsten carbide or ceramics. In our case, we most often use stainless steel. And then the material that you're processing is in a liquid nitrogen slurry living in between all those bearings or that grinding media. Now, depending on the type of material, you're going to have different effects as a result of that. But that's the basic layout and setup of the system. We currently operate 2 mills. We actually have 2 larger mills already purchased that are going to be installed at our new facility that we're currently commissioning. And so we operate a research scale as well as a pilot production scale. The capacities of this also vary greatly depending on the type of material you're processing. And I'll explain a bit more about that in a minute as well. So what benefit do you get and why would someone do this to a material? So I'll start off with the most basic and arguably maybe the most boring, which is just standard particle size reduction. In many cases, materials come in a powdered form, but someone needs them in a finer powder, but that material doesn't want to break down or get ground very easily. Sometimes that's a function of the material's low melting point where it likes to re-agglomerate or melt and become a bigger agglomerate. Sometimes it's just the material is very tough, and so it like rubbers and materials like that have a high toughness that can kind of rebound any cutting and grinding that you might try to do to them. And so those are usually issues. In that case, we are just embrittling the material with the cryogenics, and then the mechanism of the milling will just break it down very quickly. So in some cases, it's that we can do it much faster. In some cases, it's that we can get to a finer particle that you could otherwise get to. The traditional application that we were actually founded on was really for the purpose of enhancing the material strength. So as one example, we took 6061 aluminum alloy, very common, and we were able to double its strength by just reducing the grain size. So while we're cryogenically milling, the impact locations between those grinding medias essentially act like a forging, where every little particle is going to get forged, reducing the grain size of the material. So in the same way that a forged variant of a given material will be better in mechanical properties than a cast version, or a heat-treated version of a steel having a finer crystal structure will have a harder and stronger mechanical property than its annealed or large grain counterpart, we can take that same Hall-Petch relationship and extrapolate it and control the microstructure to a much finer degree. So it essentially adds new tuning knobs to every given material because we can now control the microstructure at a much finer level than ever before. The area that we probably see the most applications in is just in the kind of a different version. In that example, I was not changing the chemistry of the material where we're just changing the microstructure. But another capability of cryomilling is the ability to change chemistries in addition to the microstructures, where we can create custom alloys. As an example, we have one customer where we develop 5 new variant alloys every week at different scales, where they have a large design of experiment with different alloy compositions they'd like to evaluate for their very specific application. And we can just starting from powdered materials and raw constituents, we can just create whatever alloy composition you want very rapidly. And beyond the ability to mix materials you could normally do in a melt, we have the additional benefit of not being limited by certain limiting factors. For instance, if you try to historically melt or add a very low melting point and low vaporization point material, if zinc is an example, into an alloy system that is based on a much higher melting point material, you can have the low melting point and vaporization point material vaporizing before it can even be alloyed with the materials that haven't even liquefied yet, causing a lot of limitations. And then that is exacerbated even further when you start adding hard face or ceramic particles, things that might have different densities that might either float or sink in a liquid melt, in the case of metal matrix composites or oxide dispersion strengthened systems. And so we can really just create whatever type of chemistry with whatever kind of reinforcing particles you want, homogeneously blended very rapidly. And so the speed of iterations in developing that is very, very beneficial. And then you can always follow up with additional conventional thermomechanical processes or heat treating parameters to further optimize your material properties. And of course, last, very similar to the first one, which is moisture and heat sensitive materials. Some materials can be processed relatively easily, but they're just particularly sensitive to moisture or oxygen. There's usually some other options as far as processing, but again, given that we are in a liquid nitrogen slurry, there is zero chance of any oxygen absorption coming in. And that localized temperature increases that are the result of the grinding are kept very, very low given the cryogenic environment. So what does the material actually look like? So there is many stories. This one will just be covering an example of starting from a spherical powder. So we don't have to start from spherical powders. We typically start with materials in this process in conventional powder, thermal spray type grade powders from 20, 30 microns up to 200 micron type range, similar to the additive manufacturing type starting materials. But again, sometimes we're running pure ceramics that are just crushed in a regular shape already. But this is just an example for a light material, an aluminum in this case, that started off with spherical atomized powders. As we start to melt, those powders are going to get compressed and smashed in between those balls, like I mentioned, and they're just going to pancake out as you'd expect. In the first half hour to hour, they're going to start to look like kidney beans, and then they're going to start to flatten out into these flakes. Then as the milling continues, that flaking aspect ratio is going to get higher and higher, thinner and thinner sheets. And then as those sheets start to stack on top of each other, they're going to be cold welded together. As the material gets stronger and is forged and stronger, those structures are going to get stronger, and therefore they're actually going to start to agglomerate back into irregular shapes. This process is, again, going to be unique to the material systems. If you had a really hard material or strong material like a super alloy, this result will happen faster given the stronger nature. The milling parameters, the speed of which we're milling, the type of milling, the media we're using is all going to have an effect on this. But the main message here is that we are able to control the powder size. And in this case, we're actually keeping it a conventional size, which is an important point. So even though we are a nanotechnology company, we can control, when desired, the microstructure. So here's a piece of one of these powders that's been cross-sectioned. And we can see that we have a very refined grain structure into the nanoscale, as well as these hard phases that have been introduced, in this case, aluminum oxide inside of an aluminum matrix. And so we have a very uniform distribution of nano particulates, nano grains, but the particle sizes are conventional in the several microns, 5 to 80 microns in this case. We do that on purpose because in the case of light alloys and most metallics, if you decrease the particle size and you also don't have any oxide, that is a recipe for a very reactive material. And in many cases, it can become so reactive that it becomes pyrophoric, meaning that it'll just spontaneously combust as soon as it meets oxygen for the first time. So in our world, we prefer not to make nanoparticles. And in the case of reactive materials, we go through great lengths to make sure we don't. We get the properties of nano without having to deal with the dangers of the nano. And in this case, of course, since we're dealing with just standard metals in powdered form, all of the standard powder processing secondary applications apply, and we've done work and or supply powders for all of these applications. Just a few that people would be most familiar with would be hot isostatic pressing, which is great. We used to hip everything prior to getting into SPS, which I'll cover in a minute. Standard hot pressing, again, hot pressing is fine, it has its place, but it's essentially the kind of rudimentary version of spark plasma sintering. Just press and sinter, cold isostatic pressing and then sintering, metal injection molding, various types of thermal sprays, cold spray. Sometimes these materials are just used as pigments or catalysts. Sometimes they can be used for composite fuel cell materials, and of course, additive manufacturing. So, cryogenic milling. As I mentioned before, in dealing with light materials, light alloys, aluminum, magnesium, titanium, they tend to be reactive and very exciting when you're milling them. And so therefore it actually motivated us. We had a few small learning experiences in the early days. And so therefore it motivated us to actually develop some systems to do this in a more safe and economical way. So we actually have a patent on being able to produce materials and with cryogenic milling in a safe manner. In some cases, I mentioned how the materials are usually in a liquid nitrogen slurry. That's true, except for in the cases where the material likes nitrogen. Typically, it's inert and doesn't react with too much, but some materials like nitrogen. And just from a material property perspective, we need to mill in liquid argon. Argon being substantially more rare and thus more expensive, that becomes cost prohibitive. We have a system that can mill in liquid argon at the economics closer to that of liquid nitrogen, while also mitigating the dangers associated with producing the fine grain, fine particle sizes of metals. This is an example of a large-scale attrition milling setup. So this is the same scale mills that we have. This is not our facility, but it's to point out that just because the process in many cases is done in a batch, there's many commodity type products that are actually milled in this exact fashion, both cryo and non-cryo. This just breaks down the economics a little bit, as you can see. So spark plasma sintering. So now that we have our enhanced powders, they can either be custom alloys, custom MMCs, or oxide dispersion strengthened materials, or maybe they're high enthalpy alloys that have very unique chemistries. At this stage, how do we consolidate those powders into a solid form without losing all the properties that we may have put into them, without melting them? Maybe the materials are just very hard to consolidate in general, like high temperature ceramics. That drove us to discover and implement spark plasma sintering. And so this is the basic layout. And the most important thing to remember about spark plasma sintering is that there's no sparking and there's no plasma. I think early on, the process is done in a vacuum, and many of the original originators of the technology assumed that since we're putting a voltage potential difference in between the material under a vacuum, that's typically a recipe for plasma. However, the voltages are very low, and therefore more studies have been conducted in recent years, and it's pretty unanimous that there is no sparking or plasma. So a more popular and maybe more accurate name is field-assisted sintering technique. And there's probably 3 or 4 other names that different labs and universities have coined for the same exact technology, which is fine for novel, paper writing, but is a little bit of an extra challenge for us on the commercial side, as it scatters much of the positive results that have occurred over the last decades. So, as I mentioned, here's the basic setup. So typically we're going to be sintering in a vacuum atmosphere, but usually after an inert gas flush, nitrogen or argon. As I mentioned, you'll see here that we have our powdered material. In this case, it's in a cylindrical die. We're applying uniaxial force, and then we're going to pulse that current. So there's those sparks that don't actually exist in real life, but they help visualize the localized temperature increases on the particle boundaries. And so it's a very important differentiator compared to other sintering technologies. We are actually using the material itself or the tooling, in the case of a non-conductive powder, as the heating element. So given there is no heating elements in the furnace, that gives us an extreme versatility. And that allows us to have no theoretical maximum temperature, The highest temperature is really just the graphite itself or the material. We often run north of 2000 degrees Celsius. There's just not too many applications needing higher than that. But we also don't have a minimum. So in this case, we can actually apply very low pressure temperatures, and we've done lots of work on things as low temperatures as polymers and reinforced polymers. Since we're adding pressure and temperature via the electrical current discharges independently, we can also produce not only very high density materials, but very low density if we want to. And that's actually a growing need for things like heat pipes and heat sinks and catalysts and filters, where we can get very strong interparticle bonding, but without collapsing the pores inside by having a very low or minimum pressure. And we can get a very strong mechanical bond between those particles, allowing the final product to be an engineering material without having those porosities, as I mentioned, keeping a very high surface area and tortuous gas paths through the material. So one of the benefits of SPS beyond that is because we are heating the material directly and we're not just heating up a giant box and waiting for that heat to soak in, we also get much faster cycle times. And so in the case of, say, hipping, you might have to hold your material at 70 or 80% of the max of the melting point for several hours, where we start off with about 45% of the melting point as a target for sintering at 5 to 10 minutes. Some materials and larger dies require longer times, but it's substantially faster, which in many cases results in savings exceeding 90% energy savings. So our cycle time is faster, so we make more parts faster, and it costs us 90% less in energy. This is a very strong point in our European markets, where energy consumption is actually a part of all products write-ups. So they're monitoring energy at a much higher level than we are here. But we have lots of customers now who are evaluating SPS not for special properties, not for anything special other than just energy savings and thus cost savings. And one area that I have to always make sure I remember is the bonding and functionally grading materials. In many cases, we're not actually consolidating powders into a solid, but in many cases, we're actually just bonding solids to other solids or powdered materials to solids and various combinations of that. The heating mechanism and that electrical current discharge, it lends itself very well to bonding of materials together while maintaining their original structures and not destroying them. So it's actually quite amazing what can be done in that regard as well. So what kind of applications and who does this for what? Well, there's some of the more basic ones are just doing basic wafers for things like PVD coatings, physical and chemical vapor deposition targets, cathodic arc deposition targets, where you just need a pure material, maybe hard to sinter, maybe not, in a very pure form that's sintered for coating applications. Another area that we see a lot of gains that are unique to SPS is in the world of thermoelectrics. Not quite 100% sure on all the fundamental mechanisms there, but essentially there's essentially a little bit of a secret sauce when it comes to thermoelectric materials and their ZT properties when consolidated with SPS. I presume it's something to do with the electrical current going through. And for those who aren't familiar, thermoelectrics are a wonderful phenomena based on the Peltier effect, where essentially if you add electricity to one of these cells, one side will get hot and the other side will get cold. If you put a heat sink on the hot side, then that's a system and can be used for small scale refrigeration. And in reverse, if you add heat and you allow the other side to be passively cooled, it'll generate electricity. And so these are finding a bunch of homes in everything from remote location power generation to energy harvesting from other industrial processes. Here's an example of dissimilar material bonding and some net shaping, which I'll get into more. But here's an example of a part that we sinter with 3 different materials that are all bonded together with no brazes, no welding, no melting, no other materials, with hermetic seal in between them. And we make it in a net shape as a ring, so we have no wasted materials in the inside or the outside, and that comes out as a final product in that form. And as I mentioned, sometimes these are made with powders between solids, sometimes they're multiple solids, and any combination there between. Another area that's showing a lot of interest recently is the net shape manufacturing. And so with SPS, we're not limited to just doing what's possible with the tooling. With some other technologies, in this case, it was a binder jet, where I'll cover a little bit more of that, but we will 3D print binder jetting one material with a cocoon around it, essentially. And then that cocooned powder compact is then placed inside of a die with a space filler support powder, and then that is then SPS'd. And at the end of the day, the support powder is removed, and you're left with a complex geometry part that has the enhanced benefits of SPS in a fully consolidated 3D shape. Of course, that lends itself well to some biomedical. I can't share too much about what we're working on there, but obviously in the world of hard to sinter materials that can be used for biomedical and also in 3D shapes, lots of potentials there. And I touched on it a little earlier, but in the world of heat pipes and heat exchangers, so both heat pipes like these tubes here, which have low density cores on the inside, and the ability to sinter secondary components as well as bond different materials to heat sinks means there's a lot of applications, and we do quite a bit of work in this area as well. So several years ago, when I was first pitching a lot of SPS technology at conferences, I would always get the same answer back. Oh, SPS sounds nice. I've read a paper, but I want something larger than 1-inch button, so maybe SPS isn't for me. Nothing could be further from the truth. I've had the pleasure of seeing several full-scale production facilities utilizing SPS as their sintering and forming technology. There's several ways that you can actually scale up depending on the material properties, the shape of your part, exactly what your requirements are. One way is just scale, and you just go larger. So we operate several SPS units at our facility, the smallest of which runs tooling that's about the size of the one on the die there. That's an R&D size tooling. And you can see this is the die and it can go up to 2 inches or 2 feet in diameter, sorry. And that's the die at our friends at Idaho National Laboratory, where we do some collaborative work with them on a regular basis as well. And we actually have a unit that's a little smaller than this coming to our facilities as well. So one way you can make many parts is to fit multiple parts inside of one die. So inside of a unit that's this large, you can fit multiple holes inside a multi-cavity die. And each one of those cavities can also have several parts stacked on top of each other. And so in this case, every sintering run, if you had 12 and each one of them had 12, you could be making 144 parts per run in this case. Another way of dealing with higher volume demands is a tunnel type system. In this case, the process starts with the material and the die being evacuated under a vacuum, as I mentioned. It then gets preheated to a degree before the plastic range. Then it does the sintering. Then there's a cool down under vacuum so that the graphite doesn't degrade or oxidize. And then it gets purged back to atmosphere. So in the case of a tunnel type system, all of those things are happening simultaneously, and therefore the production rate is tied to whichever single part of that process is the longest, not the sum total of all of those added up together that you would have in a single stage system. So there's several of these units in Japan running for different types of components, and that's another thing that usually is not known to most people in the industry. So near net shaping, one of the additional benefits. I touched on the binder jet and a little bit of the tooling on the net shaping, but it's just, again, a recap that we can actually do quite a bit. This is a straight out of the SPS part. You can see a little bit of flashing here. You can see just a little bit of parting materials from some of the separation foils that we need to use. But other than that, you'll see the very fine surface finish, very high tolerance. So your surface finish matches your tooling. In this case, this part, if it's made out of a more expensive material, will have significant savings in lost material and in reduced secondary machining. And so a lot of work is going on in just, again, the net shape or near net shape manufacturing. And that's one of the main advantages to SPS as well. This is a bit of a paradigm shift for us. So this is hot off the press. We actually just recently partnered with a company called Aerosint out of Belgium, and we purchased one of their selective powder deposition units. And so here's another way to integrate additive manufacturing, combining it with spark plasma sintering. And so what this unit does is we have the ability to, you'll notice the 3 different colors on the rollers. As these rollers go back and forth, the cavity is increased in size, and these rollers can deposit each one of those materials very precisely. With a pixel size of about 200 microns by 80 microns, we can deposit very specifically powder A, powder B, and powder C. Now, in some cases, all those powders might be sintering together to make a composite component, which might have built-in heat sinks, built-in channels, things of that nature, different materials bonded to each other. In some cases, one of those materials might be a support material that does not sinter to the material, but then is removed later, leaving you with a 3D shape. And in some cases, you get a bit of both, where we can do different materials on top of each other bonded, also in a 3D shape. And so for us, this is a bit of a paradigm shift. It's a great way of being able to lay down very uniform, controlled thin layers, as well as I mentioned, making intrinsically built cooling channels, heating channels, internal geometries that you couldn't make any other way, but also getting the benefits of SPS for the consolidation. Another one of the collaborators we have is a company called Normat, and so here's another example of that binder jet turbine blade. So they also did this. The other one we did in collaboration with our friends at San Diego State University. This is a comparable version, and here they did some micro analysis to show the densities throughout the part. The bigger aspect that we work with them is on the modeling side. So as you scale up, here's an example, some screenshots of the heating profile of a very small die. In this case, you'll see there's not really much to look at. The heating happens very uniformly, and there's not much to worry about. As the parts get larger, as the tooling gets larger, and as the geometries become more complex, this uniformity ceases to exist, and you need to plan for that. If you have a very asymmetrical tooling, you can end up with hot spots or cold spots, leading to non-uniform consolidation. And this modeling software allows us to predict that before investing in large, expensive tooling, enabling us to mitigate those issues and ensure proper densification. So as a recap, what do we do in the world of SPS and FAST? Well, we offer toll services. So often we have customers coming to us that are saying, hey, we actually already have an SPS, but we can't make a part big enough. Can you help us make a bigger part? Yes, we can do that. Or, hey, we have an SPS, but it's too big and we don't want to waste that much material making a bunch of samples. Can you make a bunch of smaller R&D samples for us? Yes, we can do that. We are interested in evaluating SPS to replace our current technology, but before we invest in the equipment, we'd just like to run some proof of concepts and do some testing. Yes, we can do that. And then once you are ready and you decided you do want some equipment of your own, then we offer equipment sales. So we actually are the official exclusive representative in North America for Suga, which is the Japanese equipment manufacturer. As I mentioned, we work with several other manufacturers in SPS and around SPS for larger equipment and support equipment. And so we will actually coordinate and get you the equipment you need, all the way from a lab scale all the way up to full production. Once you have equipment of your own, then we offer the consumables. We make all of our own graphite tooling in-house up to a certain size, but we supply it for an array of users from, again, national labs to universities. And once you're operating, we will offer technical support, including training of your staff, as well as retraining and or equipment maintenance as needed. So this slide actually needs to be updated shortly because we actually have 2 new units en route. We have one that lives in between this. So these are our nostalgic units, and all these trial numbers need to be updated. They're probably about double this now, but currently we have a unit that we call a ±1 inch. The temperature that you want to go to and the pressure that you want to go to will dictate the maximum size. So that's why it's approximations in both cases. So we have about a 1-inch machine and about a 7-inch machine. Both of those will go to essentially that same max temperature, given there is no real max temperature. We call this one more of the semi-pilot production and this one more of the R&D machine, but sometimes production means small parts as well. So we do have the ability, and we as a standard handle and load all of our tooling in inert atmosphere and glove boxes. For some commercial products, we won't by design. If the commercial product will not be doing that, then in which case we will do our developments according to the production plan. So as I mentioned earlier lightly, we also have a nice ability to make one-stop shop for doing prototyping. So we do have a nice setup with some wire EDMs, some sinker EDMs, some mills, and some lathes, as well as a nice little testing facility, which I'll talk about. But this is really nice for some of our less established customers who might not have a lot of capabilities. And even those who do, sometimes it's just nice to have everything come from one shop. So often we will be just producing test coupons, test samples, but often we're actually making prototype components as well that'll actually go straight into testing for the final applications. As I mentioned earlier, we have a nice little testing unit, testing lab. Again, nothing compared to our friends over at, say, Lift as an example, but it is nice enough to get us by. So we do offer, obviously, laser particle size analysis. That is very critical in all of our milling efforts. So whenever we do milling trials and R&D runs, we always offer a nice comprehensive report with before and after particle size analysis. We have the ability to do some smaller scale planetary ball milling for very small samples if you want to do mass spec on things like that. And of course, all the standard mechanical testing, tensile compression, transverse rupture strengths, hardness, micro hardness, surface roughness, and all that. And again, it's just nice for those who don't have these things that we can provide that as well. So applications. I kind of hinted at this earlier, we work in fundamental material science, and so we literally have customers and applications that span every industry and application imaginable. Most materials, I think, materials are always the constraint in human development, to the point where we define the ages of man based on the materials we have, from the Stone Age to the Golden Age, the Bronze Age, and the Iron Age. So nothing really changes. Our ideas are limited only by our materials in all of these sectors. And essentially, we have active work in all of these areas. And it's never a dull day in our offices and labs because there's always something interesting coming up new. And that's essentially what we do. And so if there's any questions on any of these technologies, then I would be happy to answer some of those questions.
Thank you for joining Liftoff Webinars, where we propel American manufacturing into the future. Stay tuned for more informative webinars that have the power to shape tomorrow's manufacturing landscape. Discover more about Lift, our groundbreaking projects, and membership opportunities at lift.technology.
Thanks, Chris. Appreciate the great presentation. From the Stone Age to the Golden Age, it was a lot of valuable information you shared. We do have some questions coming in. So again, I'm Christine Longroy, Senior Director of Ecosystem at Lift. Thank you everyone who joined us today. So I'll kick off the questions with our first one that came in. Chris, it says, why go through powder metallurgy if you don't need to?
Well, that's a very good question, actually. And if you really don't need to, then don't. I guess the biggest advocacy against going to PM would be pure scale. So if you have an established alloy system that's being made in large volumes in a liquid melt and that's economical and it's getting the job done, then yeah, there would be no reason. The typical reason that we do this is to go beyond stoichiometric limits is one example. I touched on it a little bit in the presentation, but in one example, I use the water and sugar example. You can only add so much sugar to water before eventually the sugar doesn't go into solution anymore and it deposits. You can heat the water up and get a little bit more to dissolve, but that's about it. you've reached a limit. With powdered metallurgy, I'm dealing with ice and sugar, and I can blend them as much as I want into any ratio I want, and then I'm going to compress it and freeze it, and now I have a block of 50-50 sugar and water if I want. The same logic applies, especially in the high enthalpy alloys, and again, when you deal with materials that can't play well together in a liquid melt. So yeah, it is on a as needed basis. So speed of development, sometimes those liquid melts are really large and you can't even do a trial without going to a few thousand pounds. Speed of development, limitations on solubility limits and or hard phase densities, high and low temperature materials. And those are really the primary reasons.
Thank you. Another question, what are your customers currently using your SPS or cryomilling processes for?
Okay, I got to tread carefully, I guess. Obviously, almost every project we do is under a lot of NDA scrutiny, and so we can't share too much. But we have customers in energy storage for batteries, large scale industrial battery storage. We have customers in military working on, again, rocket propulsion systems, high temperature leading edge materials. We have customers in the green energy space, developing carbon sequestering, capturing carbon out of the atmosphere. Literally, they could be for anything. So our current customers those are probably the areas that we're most active in at the moment. But it's everything from armament materials, defense materials. It's really all over the place.
Thank you. I think that answered that well. Another question, how does SPS compare to current sintering or bonding techniques?
Well, again, I kind of touched on that in the presentation, I guess, without defining the current. I can't make too many broad statements, but because of the unique benefits will be unique to the comparisons we're trying to make. But in the case of, say, using a brazing, while not having to introduce a second material, guaranteeing the hermetic seal, the avoiding a secondary process, that's often the case. We're able to encapsulate and reduce or eliminate any deformation to the material. In one example, we had two sheets, one of which has a 50 by 50 micron channel that's carved in it for a reason. And then we can diffusion bond another material onto it and leave that channel open inside. Whereas if you were trying to use a braze or a liquid bond, it would infiltrate into that gap and then you'd have a problem. So that's one example. Higher temperature bonding of materials that maybe there are no brazes for that temperature. So it's just a technical limitation where we can just diffusion bond different materials. Sometimes that requires intermediary layers, making what's called a functionally graded material. So again, usually it's a needed basis. If brazing your copper pipe is working fine and you're soldering, then yeah, we're not going to be trying to SPS copper piping in houses anytime soon. But for more complex applications, it's definitely advantageous.
Thank you for that. It looks like that's the last of the questions, Chris. I think your presentation was very comprehensive, informational, insightful. This presentation will be available to be posted after this. It looks like there is one question that just came in, so let me just see if I can have a look at that because we have a few more minutes. So let's just. Actually, we did cover that one. So we're all set. So Chris, thank you very much. Appreciate your expertise and joining us for the Liftoff webinar today.
My
Everybody
pleasure.
have a great okay, thanks, Chris. Everybody have a great afternoon.
Take care.